Good day. I am Joffrey Menjola and I will be presenting my project, which is Muller's method and forward difference method in Phyton. So first, we will be discussing the Muller's method. So before we go over the Phyton, first let us go through some concept. So it was first presented by David E. Muller in 1956, and Muller's method is a root-finding algorithm, a numerical method for solving equations of the form f of x is equal to 0. Muller's method is based on the secant method, which constructs at every iteration a line through 2 points on the graph of f. Instead, Muller's method uses 3 points, constructs the parabola through these 3 points, and takes the intersection of the x-axis with the parabola to the next approximation. So here is the formula that is used for Muller's method, and we are given the function of x and the points xo, x1, and x2. So first, we have to find x sub 1 minus x sub o, and then x sub 2 minus x sub 1, and then we have to find do and d1, and then here we have the formulas for a, b, c, which is then plugged into this equation. So the plus and negative sign here is positive if the sign of b is positive and negative if b is negative. So for the Phyton code, we'll be switching to Phyton. So here is the code for the Muller's method. So first, we defined the function as Muller, and then we designated the variables that we will be using, which is the function, the 3 points, and then the number of iterations. So here we have plugged in the equations such as the x sub 1 minus x sub o, x sub 2 minus x sub 1, and then d1 and d2. And then we also have the formulas for a, b, and c. And then if b is less than 0, then it will be negative in this equation. And then if it's not negative or positive, then we'll be using the positive sign in this formula. And then the x3, which we will get, will now be the x2, and then the x2 will be the x1, and then the x1 will be the x0. And so it will be ready for the next iteration. So here we have the code that displays all the parameters so that we can check. And then we added a zero division error so that when there is a zero division, it will stop at that iteration. And so let us run the code for Muller's method. So let's open it up with Phyton. So here we have a sample equation so that we can proceed faster. So we type in the function, and then it will ask for the 3 points. So we will just type that in, 4.5, 5.5, and then 5. So and then it will ask for how many iterations we want. So let's say up to 3 iterations. And then the code will display the parameters and the root for iteration 1, and then and so on until the 3rd iteration. So to check this, here I have the Excel file of Muller's method, and here we can see that by checking the first iteration, we have the same fxo, the same fx1, the same fx2, also the same values for ABC, which is 15, 62.25, and 48. So and then we have the same root, which is 3.976. So we have 3.976. So now let us try another example. So then we have the initial points 1, 2, and 1.5. So 1, 2, and 1.5. So what happens if we input a large number of iterations. So what will happen here is it will stop when there is a zero division error, and in this case is after 6 iterations. And checking here, we have 1, 2, 3, 4, 5, 6 before a division error, and so therefore it stopped at 6 iterations, and the root is 1.32471. So 1.32471. And then now let us go over to the forward difference. So again, let us go through some concepts. So difference approximations of derivatives can be used in the numerical solution of ordinary and partial differential equations. We use finite difference, such as forward difference, methods to approximate derivatives. So here is the formula for the forward difference given the function, and we are also given x and h. So for the Python code of this, so first we imported the necessary libraries that we will be using, and then we defined the functions, the code fw difference, and then the parameters are the function, the x, and the h. So here we have the formula for the forward difference, and then when we run the code, we will be checking it with this, which is the example given to us. So forward difference. So we have this function. So let me just input it. It will ask for the x, maybe 0.5, and then the h is 0.015, and then the output will be 6.35966, which is the same here, 6.35966. And so we will just type exit to close the program. And then that is it for my project, which is Muller's method and forward difference in Phyton.